Here's a quick video segment that explains the way in which a yo-yo descends when released from rest. In other words, what's the acceleration of a falling yo-yo? Now I suppose what I'm about to draw isn't really a proper yo-yo. This is simplifying things a bit too much. And you've seen videos on this before. I want to imagine a device that's kind of like a yo-yo. It's just a solid disc with a strap wrapped around its perimeter. And then when released from rest, the yo-yo unwinds, and as it descends, it gains both linear velocity and angular velocity. So I think we've already solved this problem a couple times. We did it once using conservation of energy. Then we solved the problem a second time using the idea that net torque is equal to I alpha, and we assumed that the axis of rotation was at the center of mass. So I want to show you a third way that we could solve this problem that also involves identifying the net torque acting on the system, but imagine a different axis. Imagine, and it's not hard if you try, it feels like a John Lennon song, doesn't it? Anyhow, imagine that the axis of rotation is here. So it's kind of like if you turn your head 90 degrees, it would almost be like looking at a disc that's rolling along a strap. And at one point in time, point A is the point in contact. Point B is still a little bit behind, and point C is up here. And by the time it's rolled to position number 2, now point B is the point of contact. Point A has moved here, and there's point C, and on we go. Eventually, point C becomes the point of contact. And so when you look at it like that, it would be no different than having a wheel that at one point was here with point A making contact, and there's points B and C. Now point B makes contact, A has already rolled along, and C is about to be the contact point. And yeah, as it moves a little farther down the line, now C is the contact point, there's B, and there's A. So at any given instant in time, kind of gives the appearance that the wheel is hinged about a contact point, albeit an ever-changing contact point. So whether we picture it as something rolling horizontally or a disc that's unwinding on a string, there's no reason why we can't think of the axis of rotation as that contact point between the string and the rim of the unwinding disc. If you need to review, I encourage you to press pause, go back, and find the videos where we derive the equation for the acceleration of this system using conservation of energy and using torques when considering the axis at the center of mass. We found the same result in both cases. What we found was the acceleration is just equal to 2/3 g. So how can we do that with a different axis? No problem. Net torque equals I alpha. So let's draw a rigid body diagram. In all of our rigid body diagrams, make a very clear indication of where you're picturing the axis of rotation and label it. So I'm going to put an X right there and label this as the axis. Okay, so that'll help us measure all of our lever arms. So now we want to show all the forces. And this is a rigid body diagram, not a free body diagram. So where the forces are applied is critical. We know where the tension is applied. The tension in the strap pulls straight up from the edge of the disc. And gravity acts at all points. Gravity pulls down on that chunk of mass, and that chunk of mass, and that chunk. But we've stated before that the end result of all that is as if gravity is a single vector acting at the center of mass. We know to draw the vector labeled as mg greater in length than the upward vector that we labeled as t, for the simple fact that we know its acceleration is going to point downward. So let's see if we can identify what's the net force on this system as well as the net torque on this system. Well, net force is just going to be mg minus t, which means ma is mg minus t. The net torque depends on both force and lever arm factored together. And if anything, we need to identify which forces are torque producing and which are non-torque producing. So the first time we solved this problem in a previous video, we said that the tension was non-torque producing, or I'm sorry, we said that the force of gravity was non-torque producing and that the tension was the only force that produced a torque, because gravity, after all, acts at the center of mass. And so if we think of the center of mass as the axis of rotation, there's no lever arm to go with that force. Well, here we're saying this contact point is the axis of rotation. So it turns out the tension would produce no torque about that axis. So when it comes to calculating torque, it's kind of like stating what's the rotational inertia of a rod. That's not a valid question, because the rotational inertia of a rod rotated about this axis is not the same thing as the rotational inertia of a rod rotated about this axis. So in the same way, you have to be more specific and say what's the rotational inertia of a rod about its center, or what's the rotational inertia of a rod about its end. When it comes to asking what's the torque, you have to be specific. What's the net torque about the center of mass versus what's the net torque about the X marks the spot. So let's find the net torque about this axis. mg is the only torque producing force. And torque is force multiplied by lever arm. What's our lever arm? From the axis of rotation to the point where the force is applied is our lever arm. So in this case, we might as well call it capital R, not lowercase r, since it represents the full radius of our disk. And the angle is 90 degrees. Sine of 90 is just going to give us 1. So net torque is I alpha. Here's a case where I alpha equals mgr. Now, you say, I know what I is. It's the rotational inertia of a disk. And a solid disk has a rotational inertia of 1/2 mr squared. Boo! That'll give you the wrong answer. Mistake, mistake, mistake. Do you understand why? This is a way to calculate the rotational inertia of a disk when the axis of rotation is at its center. But our axis of rotation is not considered to be the center. So you know what? This is an example for us to use that parallel axis theorem. Right? Give you a quick reminder. As long as you have an axis that lies parallel to one that passes through the center of mass, so if you allow me to draw in 3D and say this is our x-axis, this is our y-axis, then the z-axis points out of the page. So I want you to picture an axis of rotation parallel to that z-axis that passes through the rim of the wheel versus an axis of rotation along the z-axis that passes through the center of the wheel. Those two axes are parallel to one another. So the rotational inertia about the prime axis versus the original axis. The equation goes something like this. The rotational inertia about the prime axis equals the rotational inertia about the axis that passes through the center of mass plus the mass of the whole object multiplied by whatever distance you shifted the axis squared. So in this case, I is equal to 1/2 mr squared plus m, let's see, Well, we shifted the axis by a distance of r, so plus m r squared, which gives us 3/2 mr squared. So this would have been a big mistake. Instead, we say 3/2 mr squared times alpha, thanks to the parallel axis theorem, is equal to mgr. I'm just transcribing this step of work and making a substitution for the correct shifted rotational inertia. Mass cancels out. One of the r's cancels out. And we have 3/2 alpha r is equal to g. But alpha r is just the same thing as a. So a equals 2/3 g. So no matter how we do it, whether we consider conservation of energy, torques with an axis at the center, or torques with an axis at a different point, we always find the same result. So the takeaway is you have some freedom of how you want to go about solving these problems in rotation, and my advice for beginning learners is to pick as many of the approaches as you can to verify that they give you the same result until you become really confident in your work. Well, that's a simplified yo-yo. But yo-yos aren't really like that, right? A yo-yo takes a solid disc, and then if I want to make my own yo-yo, I'm going to get a hacksaw or something like this, a chop saw, and cut along that dotted line. So if I started with a solid disc like this with an axis about its center, I would say it has a rotational inertia of 1/2 mr squared. So even when I cut it to give me 2/2, as long as the axis still passes through the center of mass, the rotational inertia of this whole system is equal to 1/2 mr squared. And now all I'm going to do is get a really lightweight object. So the mass of this stick, this connecting member, is really small compared to the mass of everything else. So it doesn't really change the rotational inertia of the system, and that's the point where I'm winding the string. Okay, now that's a proper yo-yo. Now if we look at this a bit magnified, we've got maybe r number 2 is the radius of the big piece of the yo-yo, and then it's got this spool, and we'll say it has a radius of r1. So let's use the approach that net torque equals I alpha and see if we can figure out what the acceleration of a proper yo-yo is. So the net torque, if we view this from its side, what are the torque producing forces? Gravity pulls on the whole yo-yo. Let me label this one more time. That's R1, and that's R2, and we've drawn the force vector mg. But if I want to consider the center, remember I have the freedom to choose now what I want to consider my axis of rotation, and I want to go back to the case where we think of the axis of rotation at the center. I'm allowed to solve it whichever way I want. I choose to picture it this way. That means that the force mg is non-torque producing because it has no lever arm. The string is not attached here anymore. Now we imagine the string attached at a smaller radius, r1. Okay, so nearly the same solution. We have a net force equal to mg minus t, and we have a net torque equal to, this is the only torque producing force, so the torque is the amount of force times the lever arm. In this case, the lever arm is R1 times the sine of the angle between those, 90 degrees in this case, sine of 90 is 1. So our first equation just tells us MA equals mg minus t, whereas the second equation we've written says I alpha is equal to t R1. Okay, so I is equal to, well, this is the rotational inertia of a disk about its center, and we've identified it correctly. No need to use the parallel axis theorem. So this is 1/2 mr squared. Now which r? This r clearly refers to the larger radius, so I believe we mean 1/2 mr number 2 squared is an expression for the rotational inertia, and then we need to multiply that times alpha. But alpha is the same thing as A over R. Now wait a minute, which R? So as it unwinds, one full rotation, right, if we go one rotation, that's a angular displacement. Well, that corresponds to a linear displacement of 2 pi r. And that would be 2 pi r1, right? So that's what we mean here. When we relate angular acceleration to a linear acceleration, the relationship involves a radius, and it's always the radius about which the string is physically wound. So here we have R2, here we have R1. So there's the left side of the equation, and then the right side of the equation is T times R1. So we have 1/2 MA, 1/2 MA, and then if I divide both sides of the equation by R1, I'm left with an R2 squared divided by R1 squared, and that's equal to the tension. So I can make a substitution. And I can say MA equals mg minus 1/2 MA times the quantity R2 over R1 quantity squared. And then I can add that expression to both sides of the equation. Actually, I should cancel out the m while I'm at it, right? And so we have A plus 1/2 A times the quantity R2 over R1 squared is equal to G. Factor out the A times the quantity 1 plus 1/2 R2 over R1 quantity squared is equal to G. So the acceleration of a yo-yo is equal to G times 1 over the quantity 1 plus 1/2 the ratio of the radii squared. Now wait a minute. For the simplified yo-yo, we know we should get A equals 2/3 G. Well, what is a simplified yo-yo? A simplified yo-yo is just the case where R2 and R1 are equal, so we can just go ahead and call it R. So that means the quantity in this expression would just be 1 squared, which of course gives us a 1. And so then we've got 1 plus 1/2, 1 plus 1/2, which would give us 3/2. So we would have A equals G times 1 over 3/2, which is the same thing as A equals 2/3 G. It looks like that's a reasonable solution.